dreams of playing Tetris. 2048 was the first game since Tetris that, for me, I dreamed about playing after playing it. It's an interesting game of chance, and what Kazuto Oka will be presenting is a technique for automated feature selection in the form of N-tuple networks. And he'll be presenting an interesting method of learning useful N-tuple networks from play with players that are using a random selection of N-tuple networks. So thank you, Kazuto.
Thank you for introduction. I'm Kazuto from Kochi University of Technology, Japan. Today I will talk about systematic selection of N-tuple networks for 2048. And this is a joint work with Kiminori Matsuzaki. This is study about the game 2048. This game is a single-player stochastic slide and merge game. This game attracts so many people. This is because easy to learn but hard to master. The game also attracts researchers. For example, we had some AI competitions and computational complexity studies of the game. Here, I introduce the rules of the game using examples. Given 4x4 board, and player selects the directions in each turn. Slide means that all tiles move toward that direction. A player can select one of 4 directions, up, down, left, and right. After each slide, one tile is randomly put with those probabilities. In this example, player selects up, so all tiles toward upward, and then a new 2 is put. Next, player selects left, and these 2 tiles are merged to 4. When merging, a player gets the same as merged new generated tile, so player gets 4 score. A bit careful treatment is needed in this merge. First case is 3 same tile and merge first 2. Second case is 2 tiles and 1 4 tile. But merged tile is not merged in same term. Third, if we have 4 tiles of the same number, merge 2 pairs of tiles. Finally, the game will end if the player cannot move any direction, like this. So far, the rules of the game. The original goal of the game is to make a 2048. But in this study, the goal is to make the score as high as possible. Before going to computer players, here I would like to introduce a very important heuristic. It is keep the largest tile at the corner, like this. Now I move my talk to computer player of the game. Here is a short list of computer players. One of the most strong player is by Wu and others. This. Based on the temporal difference learning and expect max algorithm. Temporal difference learning is a reinforcement learning method, and it uses a N-tuple network as a feature. In the following slide, we will see that N-tuple networks is. So I will show you the details of N-tuple networks. An N-tuple network is a set of N-tuples. And N-tuple is a set of tiles attached with a local evaluation value table. Here, this is a blue part of 3 tuple. For each tuple, we assign a table of local evaluation values as shown at this slide. Given a board, we pick up the values of corresponding and then look up the local evaluation values. Since the board in the game is symmetric, so we considered 8 symmetric boards for each N-tuple. Finally, overall evaluation value of the board is simply summed. I simply calculated as the sum of local evaluation values. And given the evaluation value, the computer player selects a direction so that the sum of scores and evaluation value is maximum. These tables of local evaluation values are adjusted by the temporal difference learning over a number of self-plays. In this thing, we will omit the details of temporal difference learning. Now, the question is how to select a good N-tuple network under certain environment or condition. First N-tuple network used by Subel and Jakuski. Second one is used by Wu and others. These N-tuple networks are in fact hand-selected ones. The contribution of the paper is to propose a systematic way to selecting N-tuples. Here are concrete the research questions. First, how to decide the size of N-tuples, and second is ordering the N-tuple networks by their usefulness. Third is how do the size N-tuples and the number of N-tuples, this is N, affect the performance. In this case, we'll propose the N equals 6 and N equals 4 networks. I will talk about the size of N-tuple N. N is basically limited by the memory size of the computer. If N is equal to 6, a table requires 64 megabytes of memory. If N is 7, 1 gigabyte is needed, and N equals 8, 16 megabytes is needed. On current normal computers, 6 and 7 are the possible choices for N. After fixing size of N-tuple, the number of possible N-tuples will be determined accordingly. This table shows the number of N-tuples. Number of possible N-tuples and possible connected N-tuples. This is all N-tuples and this is connected N-tuples. Since these numbers are so large, so we only consider this one, connected ones in this study. Second question was how to order the N-tuples by their usefulness. So we have to, in this study, we define the usefulness as a partial score. Here we made two assumptions. First assumption is about independence. This means a tuple is independent from others. Second assumption is linearity. This is total score is the sum of partial scores. So Under these assumptions, we can estimate the partial scores from a number of experiments by using the least square method. Now I show the parameters of the first experiment. We randomly selected 10 tuples for each run cell place. We repeated the runs until each tuple was selected 100 times on average. Each run consists 1 million games with temporal difference running. After these runs, we estimate the partial scores by least square method for n tuples and 7 tuples separately. These graphs show the distributions of partial scores in the order of usefulness. For both cases, the top 10% tuples have large partial scores, like these and like this. So we would like to see the best or worst tuples in detail. Left side is best tuple and right side is worst tuple. Please remind the nice heuristics of the game. The corner is important to achieve the high score. In this sense, these best tuples are responsible, important corner. And this worst 7 tuple gives interesting fact. This setting. You can see this includes the diagonal corners, two corners. It is worse even though it has 2 corners. It is apparently surprising for us, but after careful consideration, it is also responsible. Oh, sorry. Here are the N-tuples used by Wu and others. It is also interesting that 2 of them are good, but other 2 are not good for in our experiment. Therefore, finding a good tuple does not necessarily make a good one. Please look at these tuples. Do you agree with these tuples are good? Okay. The first one is not very good. This one is very good. This is not good. These are not good. The second one is in fact really bad. Other 2 are also bad. So these 7 tuples have 2 diagonal corners, but it does not give a good future in this game. Someone may think to generate a bigger N-tuple by adding a tile to smaller one. Sometimes it's success, and sometimes it's not. The left is a good tuple. The upper 7 tuple is indeed good, but lower one is bad. This is also a surprising result for us. Finally, we evaluate the performance by changing the number of N-tuples. Under the limitation of our computers, we can use at most 45 6-tuples or at most 10 7-tuples. We choose the N-tuples in order of usefulness. For better learning, we execute the 6 million games in this experiment. After the experiment, we plot the 10,000 game average to the number of games and final average score to computational time for a move. This is average scores of 6 tuples and 7 tuples. With the same number of N-tuples, you can see the same number, 6 tuples and 7 tuples. With the same number of N-tuples, the smaller N got higher score at the early stage. You can see this is already improved. But finally, larger N outperforms to the smaller N. In addition, the program with 10 7 tuples outperformed that with 46 tuples. This is best in our experiment. The second graph shows the average score with respect to the computational time for a move. These lines are logistic curves with so the origin fitted to the experiment result. As we can see from the graph, in the case of 6 tuples, it hit to the peak around 25 tuples. In the case of 7 tuples, it will hit the peak at 10 or a bit more. With these results, we conclude that we should use larger tuples if the memory permits. Note that even in this 10-7 tuples case, it only consumes 20 microseconds for a move. This is 20 microseconds. Concluding remark, we propose a systematic way to selecting N-tuple networks for 2048. It was based on ordering of N-tuple networks by usefulness. Usefulness were we used 2 assumptions. First assumption is independence, and second assumption is linearity. We found the trade-off in terms of scores, times and memory, and we also found some maybe new characteristics of the game from bad 7 tuples. Our future work includes the following 2. One is to give a better assumption for the usefulness. To be honest, our results are not better than that of hand-selected ones. Other one is combine our N-tuple networks with expect-max or other research algorithms. This is the end of my talk. Thank you for listening.
Questions?
Has the smaller variant of the puzzle been analyzed where the board is only 3 times 3?
と浅見さんですか。
3×3 の場合やりました。
We don't try.
So you have to use a lot of pattern to get a better result, right?
Yeah.
Did you try to use only about 4 or 8 patterns? What is the best tuple network if you only use 4 or 8 patterns? You have tried.
色セットが8つだけ使うって決めたときに、最終ベストなものを得られたか。
それって M がいらなかった。
M がいる。
M がいる。We only tried M equals 6 and 7, so we didn't try the M equals 3 or other. M. M ですか。
M の。
ちょっ とじゃあすみません、もうお願いします。
Okay, so I'll answer instead of him. So, yeah, in this study we try to make a method to select the tuples for any n. N is the number of tuples. So actually here it shows that if we limit the number of tuples, we should make the last one. Yes, yeah. So that one proposed by Wu is much better than ours. That means we have some room to improve our method to select the fixed number of tuples.
Yeah, because in Wu and others' experience, I forgot to introduce myself. I am a student of Professor Wu. In our experience, we want to reserve the memory for our experiment search, so we only select few tuples. We think that if you can select only 4 or 8 tuples, so the memory can be used for searching.
Yeah. So actually, in your result, so the score is get a peak and set some number of tuples. So we need to.
Just a basic question. Are you still on, when you talk about a tuple? Does the tuple definition of tuple include shape and location?
Yes.
Okay.
Yes.
So you could have the exact same shape in 2 different locations, and that's 2 tuples. Then.
Yeah.
I
thought you did some symmetry as well.
Yeah.
Yeah. So the top row is different from the bottom row? The top row is different from the bottom row? You don't take into account symmetry?
So symmetry means just a rotation reflection. So just writing is different.
So this is just a conjecture. I'm curious what you think about this conjecture and possible follow-on work. Maybe that the reason that Wu's N-tuple networks work well is because the independence assumption doesn't hold. That those compact blocks across 2 rows, one of them considers what's going on at the top and then the top corner. But once you get beyond the low scores and it starts to be more important to consider the configurations in the middle, that's where the weak tuple works nice it's a complement to the tuple that's along the top. And so one thing that I'm thinking is that a possible next step would be to look for best complementary tuple pairs to try to tease out the dependence. And I'm wondering whether you have any ideas in regards to being able to identify complementary pairings of tuples so as to come up with better groups. Any ideas there?
組み合わせについてやるうまい方法あるか、なんか思いつくかって言われてるから、イエスかノーか。
We already tried some count corners and some around centers and others, but the results are not good. So we don't have good idea now, but we try to improve more.
Time for one more question.
Yes. So you said not all extensions of a smaller tuple is a good tuple. Like the example you had with the 6 extended to 7. Is it more interesting the other way around? Like if you have a good 7 tuple, or all the 6 tuples in it good as well, that means if I have a good 6 tuple, is there a good extension? And this way you could guide the search. Like you first look for good 6 tuples and then try and see if any of the extensions are good.
7タプルから1個抜いたらいい6タプルができる。こっちの方が正しい。I think maybe true, the conjecture, but we haven't checked that fully. So we will check later.
Thank you.